Okay, it's 11. Christy, Maria, Brian, Mark, you guys ready?
Yep.
All set.
Okay, great. So let me welcome everybody to our first ECS and Cloud Feedback Mini Symposium. My name is Andy Dessler, and I'm at Texas A&M, and I'm one of the organizers. We came up with this idea of doing this after discussion between a bunch of colleagues on Twitter after the EGU meeting. But I've been thinking about science and travel for a while now. For scientists, travel is one of the perks of the job, but I'm sure everyone knows the enormous carbon footprint that's associated with it. This is problematic for me. I don't want to cause climate change because I know how bad it's going to be. I also think that travel represents one of the points of inequity in science. Some people are able to travel a lot, while other people, whether for financial or personal reasons, can't. And this can have a big impact on careers. So I've been thinking about remote meetings and wondering if they were very good for a while. And when the pandemic occurred, as terrible as it was, I thought it made a nice natural experiment to test out whether these remote meetings were good and whether perhaps we should have more of them instead of in-person meetings. So that's kind of the motivation for this. Our mini symposium today will have 3 speakers, which we'll introduce to you before they speak. Before I do that, though, I just want to go over a few rules. All of you are muted, and you should be unable to unmute yourself. That assumes, of course, that I set that correctly, which is not guaranteed. But we do want discussion. So if you have questions, type them into the chat box. So, even in the middle of the talk, you have a question, just type it in. And then at the end of each talk, we'll go through the questions and speakers can respond. If you really want to ask a question by voice, use the raise hand feature. And if we see that, we can unmute you and you can ask the question. I don't know the best way to carry out these meetings, so we'll be experimenting with different approaches. If this approach is terrible, hopefully we'll fix it before the next one. We'll also set aside a few minutes at the end for general discussion. Finally, let me say this is being recorded. If you don't want to be involved in a recorded presentation, you should probably log off. All right, so now I'm going to turn this over to Christy Procesescu, the other organizer, and he will start introducing people.
Hello, everyone. Thanks for joining. We have about 148 participants right now, so I think we can start. So our first speaker is Maria Rugenstein. She is finishing up her Humboldt postdoctoral fellowship at Max Planck in Hamburg and is starting as assistant professor in atmospheric sciences at Colorado State in the fall. And she's going to be our first speaker. Maria, take it away.
Sure, thank you. Let me try to share the screen. Can you see it?
Yeah, that looks good.
Yes.
Okay. So I will be first arranging you guys, so I don't see you. I will be talking about definitions of radiative feedbacks and evaluate 10 different methods to estimate ECS. And I will actually suggest a new method. And this is ongoing work with Kyle Armour, and we actually don't have a title for the paper yet. So if you have a crunchy idea, let me know. So let's see. Different feedback definitions really imply different properties of how radiation changes with temperature change. So I will be talking about warming only. And here I will contrast the equilibrium, effective, and differential feedback parameter. And we have the top of the atmosphere radiative imbalance, N, the surface warming, delta T. The intersects are the forcing and the equilibrium climate sensitivity. And this gray line here is an average or representative climate model output. And the fact that the slope is not constant is referred to as pattern effect. This would be the feedback parameter here. So the equilibrium feedback parameter quantifies the difference between 2 equilibrated states. So it's the overall forcing divided by the total warming. the effective feedback parameter quantifies the change in a current situation relative to a steady state. So it's delta n divided by delta t. And then in contrast, the differential feedback parameter quantifies the covariance of n and t with respect to a prevailing state. And this is how feedbacks were defined originally, or you can think of them like this. If you think of them as a Taylor expansion of a small perturbation, this would feed into this definition. The equilibrium feedback parameter really quantifies one specific state, so there's no time dependence of this. The big strength of the effective feedback parameter is that it satisfies the energy balance equation. So this n is equal to F minus alpha delta T. But you need to know F, N, so the ocean heat uptake or the TOA imbalance, and the surface temperature change to quantify it. And both the equilibrium and effective feedback parameter are mostly not impacted by internal variability, except sometimes the effective if it's applied to transient situations like the historical warming. Again, in contrast, the differential feedback parameter does actually not satisfy the simple energy balance equation. But the advantage is that the knowledge of the forcing is not necessary, as this is really the local tension, so you only need a change in n and a change in t. It can be, but doesn't have to be, influenced by internal variability if the range of delta t over which you do the regression or estimate is too small. So the big differences in the properties, or what the feedbacks actually mean, is that the equilibrium and effective feedback parameter really describe a different state relative, like two different states relative to each other, and they're independent of how or why the warming came about, while the differential feedback parameter represents how the change came about. So it can represent a specific process or a specific SST pattern. So dependent on these properties, the feedback parameters have different uses. So the equilibrium one can be used for studying nonlinearities and forcing and feedbacks, compare models and paleoproxies if these are actually equilibrated, if that is a thing at all. The effective one is mostly used for energy balance estimates from the historical period, and corresponds to the potentially time-dependent effective climate sensitivity, or also the CES climate sensitivity. And then again, the differential one is more equivalent to using satellite observations or changes in ocean heat content, and might be useful to understand the causes of a change in feedbacks or in the feedback parameter. So I want to show now how these definitions play out in a real climate model. I'm using CSM CAM4 fully coupled for 5,000 plus years, forced with an abrupt 4 times CO2 step simulation forcing. So you see here the feedback parameter against time. The blue is the differential feedback parameter. So it changes quickly, very early in the simulation, and stays constant. And the green and the orange are the inferred and effective. So these are both kind of relating to the effective kind of are versions of the effective feedback parameter. So for the, sorry for jumping around. For the inferred one, I keep the forcing fixed and just increase the number of years in the regression. And for the effective, which is kind of a hybrid between the two, I just increase the number of years in the regression, but don't fix F. So the slope changes more. This would be the equilibrium feedback parameter, just one number. And by definition, it's the final value of the inferred or effective feedback parameter. Just for fun, this is the PI control. So all annual means of TOA against delta T, which is kind of a version of the differential feedback parameter. In the paper, we also discuss how these different feedback definitions play out in more transient simulations and 1% simulations, and how internal variability impacts these. But just for the sake of time, I'll focus now on how the different feedback estimates result in different ECS estimates. So what I show here is the same time range. And now this is the estimate of the equilibration temperature. So this is, because I'm using abrupt 4 times, I don't divide by 2 or anything, it's just the equilibrium temperature. So it's roughly double ECS. So we see again that the differential feedback parameter leads to a quicker, closer estimate of ECS early on, while the effective parameter takes longer. So all of these estimates are effective climate sensitivity estimates, but they are differently well estimating the true ECS. Here's just for reference the standard 150-year regression. So what I want to do now is looking how common methods to estimate ECS relate to these definitions, and in how they fit in the picture, and in how far some methods are better, or let's say faster, in predicting ECS well earlier on with more or less information. So the simulations I'm using are all abrupt 4-time simulation. They're all longer than 1,000 years. And they are a subset of the LongRunMIP archive. If you haven't heard of it, go to longrunmip.org and look at the papers coming out on these simulations. They're very useful. So what I'm showing here is actually now the ECS value. So I transfer from the abrupt 4 times to ECS, which is defined for doubling CO2, by dividing by 2.17. And this is a well-informed number based on first a subset of these 10 simulations and all available CMIP6 simulations or models which contributed already abrupt 2 times and abrupt 4 times. So from these you can calculate both the feedback temperature dependence and the forcing dependence on CO2 concentration. So taking these factors into account will, for these models, lead to 2.17. And you can find out more about this in this very nice paper. Look out for it, it's not out yet, by Jonah Bloch-Johnson about exactly these issues. So, Gregory, 2004, the 150-year regression. So the order is random, it's just ordered roughly according to the overall sensitivity, these models on the left. This would be Andrews, I guess, 2017. Not really quite sure who started with this, to just ignore the first 20 years in the hope to get closer to the true estimate. This is a range of local tension, so using the differential feedback parameter, which gives you a range of estimates. This would be the 2-layer model, including ocean heat uptake efficacy. So this uses the formulation of Jofra 2013, fitting this to 150 years or to 1,000 years. Then we have 3 exponential fit. This is using the Bayesian framework introduced by Cristi Prestozescu in 2017. So this is simultaneously fitting 3 exponentials to the time series of the temperature and the TUA imbalance. So you get a nice uncertainty range. If you fit the same thing to 1,000 years, you get a much narrower estimate. And then this is based on an estimate by Mike Winton recently, last year, I guess. And he averages 50 years, but starts only in year 50 through year 300. So it's linearly regressing 5 50-year averages. So this is this little star. And now finally we have the truth. So this is from the LongRunMIP paper, and the truth is actually more true-ish. It comes with caveats like truth, I guess, should come. So you see on the left...
5 minutes left.
Okay, thank you. You see on the left the length of the simulation and the final imbalance of the TUA, net TUA. So some models, let's say the MPI-ESM here, are really equilibrated, and others aren't. CNRM here on the right is, after almost 2,000 years, is still almost 1 watts per square meter out of balance. So the truth here is regressing the final 15% of the warming, just as it's still an estimate, but for the equilibrated models, it's actually the true ECS. But for CNRM, you can imagine different possible evolutions still on this 1 watts per square meter. So here comes the new method, the suggested method. This is linearly regressing year 100 through 400. So it's a large circle, and if it's on top of the true dot, then the estimate is good. So there's a few points to make here. The method spread quite a bit, more so for more sensitive models than for less sensitive models. The suggested method is less good for more sensitive models. I don't show this here, but the different methods lead to different distributions in ECS. And I also don't show this here, but the different methods explain the spread among the models through time differently well. And there's actually more methods, never ending, I guess. So I didn't cover all of them. So I want to motivate now the suggested method a little bit better. So what I show here is the fraction of the true ECS. So gray is good, just around 1. It means a small error. Red means it's overestimating. Blue means it's underestimating. And I depict this as a function of the first year of the regression against the last year of the regression. And I'm using the same simulations as before. So what I will be showing here is a range of local tangent depending on the first and last year of the regression. So gray is good, right? These are just as a reference, some of the methods mentioned before. If you just regress, let's say year 300 through 400, it's just regressing too much noise. It's overestimating or underestimating. But then on the other hand, if you regress, if you keep the information of the initial year and just regress more and more years, this keeps too much of the information of the first few years and you will never get to the truth. So I showed this before that for the differential feedback parameter for using this, which is equivalent to the local tangents here, if you get rid of the information of the first years quickly, you can estimate ECS quicker. And for the let's say inferred one, you actually you need 4,000 years to predict 5,000 years. And this is the final motivation for the precise number year 100 through 400 is actually the standard deviation. So the shading in color is only the mean of the models, and the hatching is the standard deviation, which is quite large in the early years, but then this stronger hatching is really 0.05. So that's quite good. So I would say run your simulations longer, ideally the 4 times and the 2 times, but honestly, like 200, 300 years longer might be enough. I hopefully showed that the different feedback definitions imply really different properties of how radiation changes with warming, and the implied different, take one step back. The ECS methods have implied in them different feedback definitions, and they have advantages and disadvantages. And I leave you as a summary. I know it's a hard ending, but with this very dense comparison of the different comparison of different methods to estimate ECS. So I'm happy to take any questions now or later, or also via email later on, and question and title suggestion. Thank you.
Thank you, Maria. That was a very nice talk. So if you have questions, go into the participants box and raise your hand, or type the question in the chat box. And if you raise your hand, I will unmute you. If you type your question, I will just read it out loud for you. So Andy says, why not just ask all model groups to run their models for 5,000 years?
Yeah, if you can, please do so. Compared to all the large ensemble efforts, this is nothing, right? This is peanuts. Yeah.
So I have a question. You show that different methods tend to have a bigger spread and generally do less well for the high sensitivity models. Almost all of the methods, or all of the methods, really make an assumption that the system is linear. So does that by chance suggest that the high sensitivity models, you get a nonlinearity in the feedback, or so a temperature dependence of the feedback, or sort of additional slow physics that you can't get at over the first 150 years?
What do you mean by linear? Because I don't think all the different methods assume linearity. But I agree, temperature dependence would make it harder to get a good fit based on few initial years.
Okay. So Kita asks, what is the driver of the difference in the remaining radiative imbalance between the models, and does it relate to differences in ECS or feedback parameter?
Well, I don't know, because I don't only have the model output, right, until including the imbalance. So I don't know what drives the imbalance, like partly just time. It's also the overall sensitivity, how quickly you equilibrate within 2000 years. So the models differ a lot in this. I haven't checked whether it relates to the difference in ECS. I mean, it just depends how long the model run, right? I could. I didn't check whether the imbalance in year 1000 relates to the ECS. I guess it should.
Okay. Klein21 asks, from your plot, it appears that some models are closer to true equilibrium at the end of their simulation. Does this mean that if they were run longer, that your best definition might turn out to be different than what we're recommending?
Closer to true equilibrium at the end. Well, it's just a fit based on, my suggestion is a fit based on the 10 models I have, right? And of these, I think 6, I would have to go back, 6 or 7 are really equilibrated. And for the others, if they run longer and if they turn out to, like, the true, what I call true ECS is an underestimation if the change in the feedback parameter goes on, which is likely, right? Because all the other models do still change, even if they only are 1 watts per square meter out of balance. So all I'm showing is probably underestimating the change within the final imbalance. So probably you would need more years. Yeah, you would need more years for more sensitive models, period. So I'm a little skeptical about the precise numbers because I only base this all on 10 models, right? But this is all we have. I have to work with whatever we have.
Okay, well, we have to move on, but the speakers are gonna stay on for a couple of minutes after the hour is over, and we can continue the discussion then. But in the interest of moving things along, let's go to our next speaker. And our next speaker is Brian Soden from the University of Miami. Yeah, take it away, Brian.
Okay. Morning, afternoon, everyone. So what I would like to talk about today are using emergent constraints to try to understand clear sky radiative feedback. And this is work that's primarily been done by one of my students, Hao Jahi. and one of my former students, Ryan Kramer, who's now a postdoc, master postdoc working with Lazarus at Goddard. And the content of this talk has changed a lot, even just over the last week. So I'm not sure that this title is still completely accurate, but really trying to look at understanding the processes that contribute to intermodal spread and feedbacks and the extent to which observations can be used to constrain those. And just to sort of frame the discussion, what I've shown here are the global ensemble mean, cloud feedback, and intermodal spread, and the corresponding lapse rate and water vapor feedback. So if we just look at these two feedbacks, you see on the global mean that the spread in cloud feedback is much larger than the spread in the lapse rate and water vapor feedback. It's about 3 times as large. But what's always sort of surprised me is that if you just look in the tropics, and I've highlighted it in yellow, that the spread in lapse rate and water vapor feedback is substantially larger if you just look at the tropical mean instead of the global mean. And since much of what we understand about the response of lapse rate and water vapor to warming is based on rate of convective equilibrium and a moist adiabat, you would think that the models would be more consistent in the tropics and not less consistent. And so part of this is trying to understand why that's the case. And we've known for a while that the response of lapse rate and water vapor feedbacks is strongly dependent upon the pattern of surface warming, where, and this is a plot from an old paper, where you just plot the ratio of tropical to global mean warming versus the lapse rate feedback. And so models that have more low latitude warming, where there's a stronger coupling with the surface, produce a stronger lapse rate and water vapor feedback than models that have more high latitude warming. And there's been a more recent and much more thorough study of the lapse rate and water vapor feedbacks by Stephen Poe-Chudley. And again, they find the same importance of the spatial pattern of surface warming on the intermodal spread of these feedbacks. But they, using a slightly different methodology, really sort of find the importance of local feedbacks over the southern exotropics and driving the spread in the global mean lapse rate and water vapor feedbacks. So rather than sort of a more tropical source of uncertainty, there's a more subtropical source of uncertainty in the spread and model feedbacks. And so part of this is trying to understand these two different perspectives on the issue, and also trying to see to the extent to which observations can help resolve and narrow that spread. So the whole idea of emergent constraints is, trying to identify observable variations and that can be used to constrain the long-term feedbacks. And just as an example of this, what I'm plotting here is the global mean anomalies in net incoming radiation at the top of the atmosphere from Ceres. And you'll see that there's a lot of monthly and low frequency variability, and also a longer term trend. And so what we want to know is, to what extent can we use these variations to try to understand the long-term radiative feedbacks. And to do this, we need to understand what's causing these variations. And to do that, we're going to decompose these TOA radiative fluxes from series using radiative kernels, where we use observations of the temperature and humidity profiles from airs or from reanalyses to try to reconstruct those TOA flux anomalies. And this is a comparison of the reconstructed flux anomalies versus the observed flux anomalies. So you can see that the kernel reconstructions do a good job of capturing these month-to-month variations. But you'll note in particular that this longer-term trend isn't apparent in the kernel reconstructions. And since the kernels are only using the temperature, humidity, and cloud variations to reconstruct the trend, to reconstruct the anomalies, what this indicates is that longer-term trend isn't due to changes in the feedbacks, but it's the residual is due to something else, and we believe it's actually a result of some measurement of the instantaneous radiative forcing that the climate system has experienced over this time. So this roughly half a watt per meter squared trend over the last 18 years is really an indication of the radiative forcing that's actually detectable in the series and AIRS observations by combining them. And just to better illustrate that, what we've shown is this residual in red computed using AIRS anomalies, and in blue computing using Merritt-2 reanalyses, and they're very similar. The top plot shows the total anomaly, which we refer to as a total instantaneous radiative forcing, and then we've separated it into the long wave and short wave. And just what this highlights, really the take-home point, is that this longer-term trend is really a measure of the instantaneous radiative forcing from in the long wave part of the spectrum from well-mixed greenhouse gases. And just to show in the green plot shows the trend that's computed using offline model calculations. So we can see that a lot of the variability in the long wave anomalies are noise, but the longer term trend is consistent with what we would expect from increased greenhouse gases over this period. Whereas the most of the monthly anomalies in the total IRF are due to change we think are associated with aerosol forcing. But this comes into play when we try to use the observations to infer the radiative feedbacks, and so I'll come back in a second. So we can take the kernel reconstructions and decompose them into contributions from the individual feedback terms, the clouds, temperature, water, vapor, and so forth. And then this process actually, and then regress those variations against the changes in global surface temperature to try to estimate the feedbacks. And this process actually works best for cloud feedback. And it's typically done by creating plots something like this, where the x-axis compares the interannual feedback computed from PI control simulations, and each dot is an individual model. And those are plotted against the longer-term cloud feedback computed from the abrupt 4x CO2 simulations. And this is something that this isn't new, a number of other studies have used this approach. And so what you see is that there's a very good correlation between the interannual feedback on a global mean and the longer-term feedback. And then we've put on here where the estimate from the series observations are. And so if you just very simply look at models that fall within the 95% confidence interval of the series regressions, you can say, well, we can exclude some of these lower end models that fall outside that range. And now I should mention that this observed estimate we think is actually biased a little bit low, that it should actually be about 15% higher than that, so closer to 0.8 or 0.85 in that range. And I'll come back to that, to why that's the case in a second. But you know, what's interesting here is that if you, at least in terms of cloud feedback, and I'm not going to talk about this much, but if you look at the regions that contribute to the global mean spread in cloud feedback, which is plotted here, and we can compute that just by regressing the local mean, the local cloud feedback against the global mean cloud feedback, and doing that across model space. So these maps highlight the local contribution to the intermodel spread in global mean cloud feedback. And we see that there's very similar patterns between both the abrupt and the PI control. So that suggests that even the regions that to the intermodel spread in the long-term feedback are the same regions that contribute to intermodel spread in the interannual timescale. So that gives us even more confidence that we can use these observed variations, at least for clouds, to try to constrain the longer-term feedback. But what we really wanted to just look at the clear sky feedbacks, the lapse rate and water vapor feedbacks. And when we plot just the clear sky OLR, the interannual sensitivity versus the longer term sensitivity, we see that all the models fall outside that range. And the reason for that is that the series contains the effect of the radiative forcing gets aliased into those regressions. So if we actually add the radiative forcing or account for the radiative forcing in the clear sky OLR, then we get results that are much more consistent with the range of model simulations for the interannual feedbacks. But we see it's still not a very good proxy for reducing the spread in the longer term feedback, just because there isn't a lot of spread in the longer term feedback when you look at OLR, because it contains both lapse rate, water vapor, as well as the Planck feedback all integrated together. So it's a little bit more effective to try to separate and just look at the lapse rate and water vapor feedbacks. And we can do that using the radiative kernel decomposition. And if this is a plot showing the interannual feedback, again, from the PI control for the sum of lapse rate and water vapor versus the longer term feedback from the but-for XCO2. And again, you see that these are relatively well correlated. But again, if we try to just exclude models that fall outside the observed uncertainty, we see it's not very effective, in part because the range of the longer term feedback is just significantly smaller than the spread in the interannual feedback. So in this case, it's very difficult to exclude any models as being inconsistent with the observations. And again, so to try to understand,
you got about
why
4
that's
minutes.
The case, okay. What we've shown here is on the left is, again, the local contribution to the intermodal spread in the lapse rate and water vapor feedback. And what you see there is a sort of a very interesting pattern where there's this distinct hemispheric asymmetry. The intermodal spread in this analysis still seems to be dominated by intermodal spread in the over the tropics in terms of the lapse rate and water vapor feedback. But it's clearly tied to the symmetry and with spheric asymmetry in the warming, and that's shown on the right. So on the right side, we regress the global mean lapse rate and water vapor feedback against the local surface temperature change. And so what you see is that models that have a greater asymmetry in the warming and a more retarded warming in the southern oceans tend to have a larger lapse rate feedback and on the global mean. But most of that seems to be manifest, at least from this perspective, in the tropics rather than in the southern hemisphere subtropics. So the Poe-Chedley paper, it gets a very similar result here, that it's the asymmetry in the warming and especially the role that the southern oceans play. This analysis has a slightly different perspective in that when we quantify the feedbacks using global mean temperature changes rather than local temperature changes, which is how Poe-Chedley did it, you get sort of a different perspective on which regions contribute most to the intermodal spread. But it also highlights the challenge of trying to use observed variations to constrain the lapse rate and water vapor feedback, because the intermodal spread and lapse rate water vapor feedback is being driven by something that we don't observe on interannuals. It's this hemispheric asymmetric warming that's driven by primarily changes in ocean, or differences in ocean heat uptake over the southern oceans. And that's very different than what we saw for the cloud feedback. And just last, to kind of further contrast the different behavior of the cloud feedback and the lapse rate and water vapor feedback. This is that same regression of global mean cloud feedback against local surface temperature response. And so, again, this is done across model space, so it's highlighting the patterns of surface temperature change that contribute most to the intermodel spread and global mean cloud feedback. And you see for the cloud feedback, it's primarily driven by the zonal asymmetries in warming, which is, of course, stuff we've discovered recently. A lot of papers come out on this. Whereas the lapse rate and water vapor feedback is primarily driven by the meridional asymmetries in warming. With that, just to summarize the take-home points here is that we can detect the radiative forcing in the observed record from errors in series. I think that's really sort of a testament to the stability of those data records that we can see a roughly half a watt per meter squared forcing over the last 15 years. The interannual variations provide a useful constraint on the longer term cloud feedback, and even the regional contributions to that intermodal spread are very similar on both interannual and longer term changes. But for the clear sky feedback, so lapse rate and water vapor feedback, it's much more difficult to constrain these from interannual variability. The spread and global mean feedback is damped in part because of there's this hemispheric asymmetry between the northern and southern hemispheres that offset each other. And the pattern of warming that contributes to that intermodal spread is very different from the pattern of warming that we can observe from interannual variability. And so with that, I'm happy to take any questions.
Great, thank you, Brian. So we got a question from Paolo here. How many years did you use for your PI control cloud feedback estimates?
Those are actually ensemble means of 15-year segments from each PI control run. So it was the full record of the PI controls. I don't know the details, but each 15-year segment we computed the feedbacks and then took the ensemble average of those feedbacks for each model.
Jonah asks, how are the local feedbacks calculated? Do they account for noise?
Well, the local contributions are computed by taking the global mean feedback and then regressing it against the local feedback in each region. So that's the local radiative anomaly divided by the global mean surface temperature change.
Daniel had his hand up, but I see he typed it. Have you also tried inferring the spatial pattern of the forcing from your series plus kernel method?
Yeah, we have. I don't have a slide of that. I'm trying to remember what it looks like. I know in the shortwave, you see a lot of signatures of the aerosol forcing. That's probably the most significant result in terms of the spatial structure of it. That you see patterns that are clearly associated with aerosol forcing over the last 15 years.
Thanks. And one more quick question. Yoko asks, increasing the accuracy of the observations of clear sky long wave flux may be useful?
They seem pretty accurate already, at least in terms of their stability. So I don't think that's the bottleneck here. The bottleneck is really the underlying processes that are driving the long-term changes in lapse rate and water vapor feedback are very different from what's driving the observable changes in lapse rate and water feedback.
Thanks. Andy has more of a comment than a question, but it might have to wait until after Mark's talk during the discussion session. Thanks again, Brian. And our last speaker is Mark Zelinka from Lawrence Livermore National Lab. And take it away, Mark. I will tend to let you know the chance left.
And can you hear me now?
Yes, we can hear you.
Okay, thank you, Steve, for the invitation to present. I'll be giving an update on our work looking at the climate sensitivity in the latest CMIP6 models. This is work done in collaboration with Tim Myers, Anna McCoy, Steve Butcher, Peter Caldwell, Paulo Ceppi, Steve Klein, and Carl Taylor. As you can imagine, this paper came out earlier this year, but this is quite a moving target because the CMIP6 archive continues to be populated with more models. When we published the paper, we had 27 models, and now we are up to 40. So that's what this update is about. Fortunately, most of the results are pretty much intact from the paper, so there's not a lot of changes just in the details. So basically, the way we're diagnosing this is using the abrupt 4x CO2 simulations from CMIP5 and CMIP6, and we compute the anomalies with respect to coincident PI control simulations. So we follow the standard kind of Gregory approach of using all 150 years of the abrupt 4x CO2 simulations and compute a single regression line through that plot. So this would be basically equivalent to Maria's effective climate sensitivity, effective radiative forcing, and effective feedback parameter. So the slope giving you the feedback, the y-intercept giving you the effective forcing, and the x-intercept giving you an estimate of the effective climate sensitivity. To get more insights into what drives the intermodel spread in climate sensitivity and the change from CMIP5 to CMIP6, we decompose the feedback into individual components using radiative kernels, as Brian just described one of them. We check out several different kernels, but we end up using Yi Huang's kernels based on E-ray interim because they end up yielding the smallest residuals. And we do the analysis using the constant relative humidity framework of Held and Shell. So here's the basic result from our analysis. In blue are the CMIP5 models, in orange are the CMIP6 models. The first column shows effective climate sensitivity. You can see that it has gone up on average in CMIP6 and that the spread has also increased. And we now have a large number of models that exceed the highest ECS that was present in CMIP5. So the mean ECS has gone up by about 0.5 degree. We've got climate sensitivities exceeding 4.5 in 14 of these models. And I will note that we are at 40 models right now from 22 centers, but we still expect many more to come in based on who has registered to do the DEC experiment. So we still expect at least another 60 models to come in over time. If you then look to the next column, the effective radiative forcing, you can see that that has not really changed much. It has gone up slightly and the spread has come down a little bit. So not a big change in the forcing. And then similarly, the net radiative feedback parameter has also become slightly less negative and shown a slight increase in the intermodal spread between CMIP5 and CMIP6. We break down this net climate feedback parameter into its components, the Planck, the lapse rate, the relative humidity, surface albedo, and cloud. And of course, with kernel technique, there's always some residuals. And what you see is that this slight increase in the net feedback is almost entirely coming from the cloud feedback right here. So on plots like this, I'll be showing differences of means that are statistically significant with connected lines. And if the variance has increased, I'll show arrows pointing away from the mean. And what you note in this figure is that no means are connected with lines and no arrows are present. So that indicates that actually, if you account for the fact that there's a lot of duplicate models from the same modeling center, or heavily related models from the same modeling center, you actually do not get a statistically significant change in the mean ECS or its intermodal spread between CMIP5 and CMIP6. So this plot kind of highlights the fact that despite the fact that the forcing and the feedback have really changed in really subtle ways, there's nothing really particularly dramatic about the change here, whereas the climate sensitivity seems to have a pretty large change. Even though it's not statistically significant, you can see that there is substantial increase in spread and a large number of models that are outside of the previous range. So why is that? And it's important to remember that the climate sensitivity is the feedback divided by the forcing, so it's helpful to plot those against each other to try to rationalize this. So that's what's shown here. And I've highlighted the CMIP6 models that are kind of in unprecedented territory in terms of climate sensitivity with filled colors. So you can see that there's this population of models up here that have higher climate sensitivity than any in CMIP5. And so, as I noted earlier, the forcing and feedback distributions haven't really changed much. It's really just the joint locations on this diagram that have changed. So for example, in CMIP5, if you had a really weak radiative damping or were characterized by overall positive feedbacks, you tended to have a pretty weak forcing as well. So you'd be up in the upper left quadrant. But now in CMIP6, the models that have the weakest radiative damping tend to be shifted over towards having moderate radiative forcing. So that allows them to get kind of above these high ECS isoplots over here. And you can make a similar argument for the two Russian models that have come down to be the end members at the low end of ECS. So we're interested in understanding why the mean ECS has gone up. And so there's three things that we need to look at. One is whether the increase in the forcing has caused this, the increase in the feedback, or just the tendency for this whole distribution of points to have kind of rotated to be more aligned across the ECS isoplots, as you can see here. And so we basically do some hypothetical calculations where we shift the distributions around to try to match the multi-model mean forcings, and feedbacks to estimate how much of the change in multi-model mean ECS is coming from these three terms. And so what we find is that the bulk of the change in multi-model mean climate sensitivity is coming from the change in the feedback. So over 50% of the change in climate sensitivity on average is coming from the stronger positive cloud feedbacks. The remaining part of that is 30% is coming from this change in the distribution of forcing and feedback space, kind of the covariance between the two. And then the remaining 20% is coming from the increase in radiative forcing between CMIP5 and CMIP6. So the fact that the feedback change is the main reason for the increase in climate sensitivity motivates us to focus on this component moving forward. And as I mentioned earlier, that's entirely coming from the cloud feedback getting more positive. So we wanted to diagnose why the cloud feedback has strengthened in CMIP6. We used two kind of inference-based methods to detail this. We used the web technique that allows us to separate the feedback from contributions of clouds at different heights, which we aggregate into just a low category and a non-low category of clouds. And then we also use the approximate partial radiative perturbation method of Taylor et al. To separate the shortwave cloud feedback into two components. One being the changing cloud fraction, the amount of clouds, and the other component being the change in cloud scattering or reflectivity. So those two components just in the shortwave. So this is what you get if you do that. So this is again showing the breakdown for net non-low clouds and for low clouds. And you can see that the increase is mainly coming from the low cloud component, whereas the non-low clouds have come down slightly, but are generally positive in agreement with what we expect from a number of other pieces of evidence. The reason for this decrease remains to be investigated still. But hereafter, I'll focus on the low cloud feedback, which has gone up. And of course, this is entirely dominated by the shortwave, which is shown here. And actually, the intermodel spread in shortwave low cloud feedback has increased, as you can see with the arrows pointing away from the mean. If you then break this down into the amount component and the scattering component, you can see that you get roughly equal contributions from both. So you've got larger decreases in cloud fraction in CMIP6, giving you a more positive amount feedback. And actually, the scattering feedback changes from negative to positive in CMIP6. So you used to have clouds getting more reflective, and now in CMIP6, they're actually getting less reflective on average. There's still a substantial amount of intermodal spread. If we look at the patterns of these as a function of latitude, you can see that the change is almost entirely coming from the extratropics, and most dramatically in the southern hemisphere. So you can see, especially in the southern hemisphere, where there was a peak in the shortwave cloud feedback for low clouds, that peak has gotten much larger. And the region that was negative at higher latitudes has weakened substantially. And so the change is positive and large throughout the extratropics in both hemispheres. And again, this gets roughly equal contributions from the amount and the scattering components. So then if we return to this previous plot and just show the breakdown by region, tropics and extratropics, you can see pretty dramatically that the increase is really large in the extratropics and is basically non-existent in the tropics for both the amount and the scattering feedbacks. And in fact, in CMIP 6, the extratropical amount feedback is actually larger in magnitude than the tropical amount feedback, which is pretty remarkable. And many of these changes are statistically significant at 95% confidence. Okay, so let's try to dig even deeper into this to try to rationalize why the extratropical low cloud feedback has increased in CMIP 6. And I'll just focus on the scattering component for now. And this is really closely tied to how liquid water path in low clouds changes.
10 minutes.
How many?
You have 5 minutes left. You're at 10-minute mark.
Okay, thank you. So models that have larger decreases in liquid water path tend to have more positive shortwave low cloud scattering feedback. So what we'll do is try to understand this through a cloud controlling factor analysis, which we perform on low cloud liquid water path just over the southern hemisphere oceans. And just to orient you to what this is, it's basically trying to decompose the change in the low cloud properties with global warming as the product of two things, one being their sensitivity to various meteorological variables like SST, estimated inversion strength, etc., scaled by how those meteorological controls change with warming. And so this type of analysis has been done many times now in the literature, and the low latitude studies are pretty well established and have been recently reviewed by Steve Klein in a review article. But I'd also note that this has been applied to the extratropics also pretty extensively in a number of papers. So there is precedent for applying this at the southern hemisphere latitude, as we are doing here. And so I'll note that this first term, the sensitivity, we derive multilinear regression analysis just in the PI control experiments. And then we use the climate change responses from the abrupt 4x CO2 to get the change in cloud controlling factor. So what I'm showing here is, again, this sensitivity term, the sensitivity of low cloud liquid water path to various meteorological controls. I'll draw your attention to the SST term because it ends up being the most important. Again, CMIP 5 is in blue and CMIP 6 in orange. And you can see that in CMIP 5, when SST increases, you tended to get an increase in low cloud liquid water path that was pretty marked. And now the CMIP 6 models are basically straddling zero. So on average, they're actually very close to having no sensitivity to their low cloud liquid water path to surface temperature changes. As I mentioned, these get scaled by the abrupt 4x CO2 change in these various cloud controlling factors. And so this motivates the focus on SST. It's because it has the largest signal of all these cloud controlling factors. So the product of these two will be the largest component to the change. So when we do multiply the sensitivities with the actual changes, what we see is that the SST component of low cloud liquid water path changes, again, is really strongly positive in CMIP 5 and is now much smaller and basically straddles zero in CMIP 6. So if we add this component with all of the other components in the decomposition, we get something that looks like this. Low cloud liquid water path increasing in CMIP 5 and decreasing in CMIP 6. We can check to see how well that does by overlaying the actual model produced changes in these two terms. And that's shown in the black. So the CMIP 5 is to the left of the CMIP 5 box and CMIP 6 is over here. You can see that it does a fairly decent job of actually capturing this tendency for an increase of liquid water path in CMIP 5 and a decrease in CMIP 6. And the across-model correlation is also decent from this model. So it's not perfect, but it is capturing the basic response. And so the punchline here is that the fundamental change between CMIP 5 and CMIP 6 is coming from this term, which is essentially the model physics. How sensitive is low cloud liquid water path to warming? And that's basically tied to the parameterizations. And I don't show it here, but the same story can be found for low cloud amount and for low cloud cover and the amount feedback. So it's again tied to how sensitive these parameters are to SST. Okay, so now moving into kind of speculation as to the root cause of this. It's been shown before that models that have large state liquid condensate fraction, so more liquid in their base states, experience weaker liquid water path increases with warming. And there's been experiments done where you modify models to produce higher mean state liquid condensate fraction. And they do indeed find that the extratropical scattering and amount feedbacks actually become more positive. And so that's possibly a reason why CMIP6 models are showing this, this tendency for a more positive feedback at the high latitudes. And I'll just show here a plot that gives some evidence that the models are doing a slightly better job overall in CMIP6 of maintaining liquid down to colder temperatures. So this is the liquid condensate fraction as a function of temperature, 1 being all liquid and 0 being all ice. And here's some estimate of this from observations, from LiDAR observations from space. You can see that the models have tended to shift from right to left overall in this diagram, indicating that they're doing a slightly better job of maintaining supercooled liquid down to colder temperatures, which we've seen in previous work is tied to higher climate sensitivity. The quantitative analysis of this remains to be demonstrated, though, that this is actually the reason in all the models for the increase in climate sensitivity. I think this remains to be shown, and I'm pretty confident that there'll be different stories for different models. Okay, just to conclude, the average ECS has increased by about 0.5 degree in CMIP6. We've now got values above the kind of maximum end of the likely range of IPCC in 14 of these models. It turns out that neither of these changes of multi-model mean or spread are statistically significant at 95% confidence. As I mentioned, the highest ECS values arise from weak radiative damping and moderately strong forcing. Neither of these in and of themselves are that anomalous in CMIP6. It's just the combination of the two that's kind of in uncharted territory. Most of the increase in mean ECS is coming from the positive cloud feedback, so about 52% of the increase in the mean is coming from that. And then we tied the stronger positive feedback in CMIP6 to stronger decreases in low cloud coverage and albedo. And that's entirely coming from the extratropics. And we think that this could be tied to the mean state cloud properties, but that remains to be shown more rigorously. So thank you for your attention.
Thank you so much, Mark. That was a great presentation. So we got time for a quick question for Mark, and then we're gonna open it up for a broader discussion. So Daniel had a good question. Do you get any bias from just the fact that CMIP6 includes more models than CMIP5? E.g., following the Roe-Baker 2007 toy model, if you keep performing random draws from a distribution of climate feedbacks, couldn't the mean ECS be sensitive to how many times you draw?
I suppose that's possible. You know, for some of these results, for example, the fact that there's now 14 models outside of the range of CMIP5, you know, that's not really sensitive to a sample size, I don't think, in part because when we published the paper, we actually had fewer models in CMIP6 than we did in CMIP5, and we still had a large number of models that were outside that range, the CMIP5 range, that is. But yeah, I think there could be some possibility that more models are coming in that have a broad, you know, with this large number of models, that there's a greater possibility for a larger diversity of climate sensitivities in CMIP6. But it turns out that when you do the statistics accounting for duplicate models from the same modeling center, you don't actually get a statistically significant change in the mean ECS or its spread. So yeah, it is important to do the statistics right.
Cool, thanks. Axel Lauer asks, why do some models still show a substantial liquid fraction at temperatures below 235 Kelvin where homogeneous freezing should take place?
Yeah, I think this is probably a little bit of just a, you know, this is kind of a statistical plot. So, and it's computed with monthly mean data. So I would be surprised if any model actually instantaneously maintains liquid below the homogeneous freezing, homogeneous nucleation temperature. So I think it's a little bit of smearing going on by using monthly data and aggregating that all into one plot.
Okay, well, thank you so much to everyone. Thanks to all the speakers, you did a great job. Thanks to everyone who showed up, and we're gonna let people go if they want to go, but hopefully the speakers can stick around for a bit more discussion. And I thought for this part we could try something else. We could try to have people talk, so it's not just me and Andy and the speakers talking. So if you have a question, please raise your hand, and I will unmute you.
And while we're
Christy,
waiting for that, Christy.
Stop sharing?
Oh, can I say one thing, Mark? Before people go, we very well may decide to do this on a semi-regular basis. If you're interested in giving a talk, email me and Christy. All right, Mark.
Yes, similar, if you have any other feedback for how this should be organized in the future, let us know.
Should I stop sharing, or did you want to? Is there a way for us to all look at each other like the Brady Bunch, or?
Yeah, I think if you stop sharing, but then we'll just mostly be looking at people's names.
If you stop sharing and turn on speakers, turn on their webcams, we can see you guys.
I think I've stopped sharing.
Okay, so people seem to be hesitant to raise their hands. So there were a couple questions that we didn't get to. Eric de Weaver asked, this is for Maria, I think, can every current model run to 5,000 years without crashing or producing unrealistic results?
Well, I don't know. So of the models we got for longer MIP, there's 2 which crash, but only at 8 times and 32 times CO2. And all the others look normally until the end, whatever people submitted. So in the order of 1,000 to 6,000 years. But of course, this could be biased, that the people with crashing models don't submit.
That's a fair point. There was another question from Maria, now I guess from Mark. Mark, did you look at other timescales for your estimation of F and lambda? 150 years is absolutely arbitrary and does affect the differentiation of F and lambda. In other words, how much of the difference between CMIP 5 and 6 is due to different time dependency of the feedbacks and or the separation of F and lambda?
I did it in kind of probably the most basic way possible, which is I guess the Andrews way. First 20 years, use the first 20 years for the forcing, and use the last 150 or last 130 for the feedback, or not for the feedback, but for the ECS. And actually, that didn't change the for the figure that I showed that was kind of breaking down the contributions from 50% from the forcing, 30% from the covariance. That actually didn't change very much when I redid that plot in that way. So one thing that's different in CMIP 6 is that the kink in the Gregory plot has gotten a lot smaller, at least over the 150-year time scale. So the ECS derived from the last 130 years is only, I think, 5% larger than the 150-year ECS, whereas in CMIP 5 it was something more like 10%, if I remember the numbers correctly. So there does seem to be something different in CMIP 6, and I know Yue Dong has a paper on it, looking into why that kink has weakened in CMIP 6. But yeah, for the results I was interested in terms of the change in the mean ECS and attributing it to forcing and feedback and covariance, that actually didn't change much with trying different definitions of forcing and feedback and ECS. But perhaps using one of your other definitions, it would be more sensitive.
Cool, thank you. Jesse Loveridge and then Nader Jivanji. You both should be able to unmute yourselves now.
Hi, I guess my question is mostly for Mark. In interpreting the changes between the model ensembles. How do we go about dealing with model dependence? So like groups of models from the same modeling center or so on. How do the changes that you report, are they like clearly, some of the higher sensitivity models clearly traced back to certain groups, and then maybe some changes that those groups made in their models, or is it fairly random?
You're right. There are a lot of closely related models from the same modeling centers. For example, there's now 4 different CESM2 model versions in there. 2 flavors of Wacom and 2 flavors of non-Wacom. We try to account for when we do our statistics, at least, we try to account for, we basically average together models from the same center, which is a little bit of a naive way of doing it, because there are better ways of doing it that you actually can assess more objectively how independent models are. Because being from the same modeling center doesn't necessarily guarantee that you're that closely related. And even if you're not from the same modeling center, you could be really closely related. So that's kind of the poor man's quick approach for trying to, handle this statistically. Other methods will probably find different results depending on how they handle that. But I agree that probably if you found a particular modeling center had some big change in their feedback, you could possibly tie it back to a specific change that they made. That's the hope. And I know that's something that we're looking at least here with the E3SM model.
Cool, thank you.
Nader?
Hi, this question is for Maria. Thanks to everyone for great talks. So Maria, you showed for, I think, CESM, you showed the 3 different definitions of sensitivity, time series of those sensitivities. And for the differential sensitivity, it was remarkably constant, after some initial phase of maybe, several decades. Is that characteristic of GCMs, or is that idiosyncratic for CESM? How common is that for the differential sensitivity to be so stable over the slow time scale?
So it's more a couple of decades, more 50 to 100 years, and others are slower, but in the order of magnitude of a few hundred years, because this is how I arrived at this ideal regression of 100 to 400 years, right? And even 100 to 300 would be fine. So I think the most important thing is to get rid of more than 50 years in the beginning. This would already increase the precision a lot. But then there's some high sensitivity models like the CNRM, you would probably need 600 plus years. And I don't even know, because I don't know the absolute truth.
I see, but then after that period of a few hundred years, do most models show a very flat differential sensitivity that doesn't change with time after that?
Mm-hmm, mm-hmm. Yeah.
Okay, great, thank you.
Cool, thank you. So we got a couple of related questions. For Mark, any speculation as to which particular parameter scheme change is related to cloud representation might be influencing the low cloud scattering or amount feedbacks?
I think it's probably best to actually read the modeling papers from different centers. It really varies based on centers. So there's Alejandro Bodas explained in detail what went on at the in the Met Office. The Hadley Center models. Andrew Gelman has a nice paper on what happened in CAM 6. Those are probably the best papers, because it's usually some things that are semi-related, but a lot of these things are unique to individual modeling centers. It's probably worth digging into those papers like Gettleman and Bodas Acedo. I don't know if there's any others there's probably others, but they aren't coming to mind right now that have tried to dive into the cloud feedbacks in specific models. I can see the chat. Maybe I'll just Yoko says, are you planning to look at results for individual modeling centers? and like changes in the parameterization such as supercooled liquid water amount. So with the information that I have tried to basically look at to see whether the supercooled liquid fraction curves have any relation at all to to the scattering feedback over the mid latitudes, and it's not like a slam dunk as you might expect based on our kind of what we thought was intuition about having more liquid in the mean state means you've got a more positive scattering feedback. Some models do show that when they change from their CMIP 5 to their CMIP 6 version, they kind of fit that mold, and others don't. So I think the tie to things like T5050 or supercooled liquid fraction, unless I'm doing it too naively, those linkages remain to be interrogated, I think, in greater detail. My initial sense is that it's not as strong of an explanation as we were hoping initially. Gita says, Mark, do we know how much the increase in base state liquid and better representation of liquid water path in the CMIP 6 models affects hygroscopic growth of sulfate and therefore the overall rate of forcing from aerosol and potentially the overall shortwave cloud scattering? It's a good question. I don't know. I don't really have much intuition about that either. Yeah, it's a good question, worth looking into.
We should probably wrap up at this point. So thanks to everyone who attended, and thanks to our speakers. Really well done. And hopefully, Christy and I, hopefully we'll make this semi-regular occurrence. So look for an event coming up in, maybe a month-ish time frame.
Thanks, Andy. Thanks, Christy.
Yeah,
Thanks, guys.
so long.